Howdy, my name is Salem Smith. I'm a current junior here at Texas A&M University. Today I will be talking about antioxidant polymer films and my research with them in this final update for the summer 2021 O-REU program at Texas A&M. First, I'd like to give acknowledgments to my mentors, Jordan Brido, a graduate student here at Texas A&M, and Dr. Svetlana Sukashvili, a professor here at Texas A&M, and, of course, all people who worked to make the O-REU program here at Texas A&M possible this summer. For a brief introduction and overview, my project has been centered on using in-person research using a variety of techniques and materials to test antioxidant properties of layer-by-layer films. Layer-by-layer films, for those of you who may not know, are basically polymer films that are constructed by building them up one layer by one layer, usually of two different materials. For example, we might use tannic acid and PVPON, depositing them back and forth. The goals and motivations of this project. Antioxidant polymer coatings are very useful because they can reduce swelling and inflammation, helping with biomedical implants and devices such as stents. A stent is basically a thin tube that you can insert and expand in something like a clogged artery to help it stay open and encourage blood flow. Obviously, antioxidizing properties would be very useful for this because you don't want any inflammation. We're using layer-by-layer films because they exhibit a higher diffusion for controlled release of antioxidants compared to other polymer synthesis methods, which is aided by the fact that you can tune the interactions between layers, such as by changing the pH or adding salt. Up here we have a graphic from Zhao et al. In 2013 showing this controlled release of sort of drug delivery for these layer-by-layer films. Further describing the goals and motivations, layer-by-layer films have the radical diffuse into the film before undergoing the antioxidant process, so you can control the level of antioxidant response by controlling the strength of bilayer interactions. We're using polyphosphazine backbones with our polymers, which have higher biocompatibility because they have a nitrogen and phosphorus backbone rather than a traditional carbon backbone, making them more flexible and more easily biodegradable. And of course, our main goal is to further investigate the relationship between the polyphosphazine backbone and antioxidant ability. For our materials, we're using tannic acid and gallic acid as our main antioxidants. This is because they have these phenol groups of OH, which are really useful for radical scavenging for oxygen and nitrogen radicals. We're using polymers with and without polyphosphazine backbone to compare the results. We are using both hydrogen bonded and electrostatic to see if there's any difference between those two. So our FDMP is a polyphosphazine backbone electrostatic, and our PAH is just carbon backbone electrostatic, and vice versa. Our PYRP is hydrogen bonded with the polyphosphazine backbone. Our PVPON is just hydrogen bonded. So one thing that's important to note is that with the electrostatic polymers, these are weak polyelectrolytes, so our ionization is pH dependent. So in all of these solutions, we're going to look at the effects that pH will also have on these solutions. Our methods, we will be using the layer-by-layer synthesis technique I briefly described before. We will be analyzing the thickness of the films using the ellipsometer. We will test the antioxidant abilities of the films using ABTS solution and UV spectroscopy, and we will finally analyze self-healing abilities using optical microscopy. So here are an example of some of the layer-by-layer films. The ones to the left are sort of what we would consider good films. They're more uniform, sort of shiny. The ones on the right are not so good films. They're more cloudy because they grew more exponentially and unevenly. Here is a photo of the ellipsometer. If you don't know how this works, just a brief overview. One side basically casts down a light beam. This diffracts and is reflected onto the other side, which is able to give us a measurement of the thickness of the film. This is the ABTS and spectrometer setup. On the left, we have the spectrometer results. We'll be looking for data at this highest peak in the middle, right around here, which is around 732 wavelength. Here is our solution just by itself. It has this nice blue color. Once it starts to react with the antioxidant films, it will lighten in color and become more clear. On the right, this is when we made the ABTS solution. So we took the solution and flooded it with nitrogen gas just to make sure we get all those radicals and we're not having strange results because something in there is present and reacting that shouldn't be. Here is the optical microscopy. This is the latest series of tests we've been working with. So instead of silicon chips, like I showed earlier, we have to use these glass chips so that they can be visible under the optical microscope. The optical microscope basically works by using a small, thin beam of light that you can control the voltage on, sort of change the wavelength to get a better image. And to the left are these image outputs. So for the results and outcomes, we have thickness data and graphs, antioxidant data and graphs, and some initial self-healing data images. Here is the assembly with tannic acid via electrostatic interactions when analyzing the thickness of the films. So on the left, we have the PAH, which as discussed before, has a carbon backbone compared to the tannic acid with FDMP, which has the polyphosphazine backbone. As you can see, the PAH film didn't really grow and isn't really effective. It didn't bond with the tannic acid well when we compare it to the FDMP, which grew more exponentially, and we were able to get a decently sized film within a shorter period of time. We can see similar results with the tannic acid via hydrogen bonding when comparing the PVPON at 171 kilodaltons versus the PVPON with the polyphosphazine backbone. As you can see, very similar results. However, the PVPON did grow faster than the PAH, even without the polyphosphazine backbone. So here we have our absorbance over time, which is how we're measuring the antioxidant abilities of the films. So again, these are all taken at a wavelength of 732. So here we start off what is close to just the natural solution, and then in this case, with our PVPON tannic acid, it very quickly dropped and it was effectively neutralized. Here we can compare it to the thickness. This was also the thickest film, so this is something to consider. A thicker film is likely to produce better results when it comes to antioxidant abilities, just because there's more there for it to respond to. So when we see a dip like this on the graph, that's normally indicative of the tannic acid actually sort of reacting with the solution rather than the radicals in the solution. And when we see an increase, like here, this could be because of some minor amount of swelling of the film. This is known to happen with layer by layer films if they are put in solution. But however, these results look like it didn't change too much in thickness over time. We can see a similar thing when we look at the absorbance over time for the FDMP and tannic acid. As you can see, the pH has a big effect on how thick they can grow and how fast they can sort of have these antioxidant properties. Again, generally the thicker films are able to scavenge for these radical ions faster. This is the FDMP with gallic acid. It's important to note that gallic acid is such a small molecule that, one, we use FDMP with the polyphosphazine backbone because it's way easier to bond to this small molecule, and two, there's a lot less phenol groups, so while the antioxidant ability might look smaller, it could be greater when compared to antioxidizing ability per phenol group. So that's something to analyze further with the data. Again, thickness and pH. Any increase could be because of swelling, any decrease could be because of tannic acid releasing into the solution. Finally, with the self-healing abilities of the polymers. So self-healing just means that it can repair damage. In this case, we did a thin scratch and waited for it to reform a uniform film. Our systems may show this because of the polyphosphazine backbone. This makes it more flexible, which means polymers can more easily diffuse. The molecules can more easily diffuse and have a greater likelihood to repair this damage. So initial tests are done with the optical microscope. We just begun this, but this isn't exactly the most accurate. To further analyze this behavior, I'll need to refine my techniques, and I might need to train in something like atomic force microscopy. So here are some of the initial images. This is the PYRP, which is the polyphosphazine backbone of PVPON. This is at start. This is after 1 day and after 2 days just in air. As we can see, this ability to heal is actually pretty good. This is the PYRP and phosphate buffer at room temperature. This one isn't so good. However, this could be because the scratch was made too large to sufficiently heal, or the scratch was cut down to the glass, which wouldn't give the film the ability to heal either. So we need to redo this sample. This is the PVPON without the polyphosphosine background at room temperature. Not really any big difference here. Same thing with the PVPON in phosphate buffer at room temperature. Not really any changes. Here is when we began to heat the phosphate buffer solution. Heat can help with diffusion, as being in phosphate buffer, being a salt, can also help these molecules to diffuse. Here, it looks like it's slightly starting to change, but it's a bit too early to tell, so we'll take some more results. Same thing here with the molecular weight 171 PVPON. Again, when it's heated, not really much of a change, probably because it has that traditional carbon backbone. So for the conclusions, polyphosphosine backbones seem to lead to greater flexibility, which allow greater film growth. Polyphosphosine backbones may also lead to better antioxidant release with tannic acid and gallic acid. However, further research and more testing of different systems is needed. Further research is also needed in the self-healing abilities, as we don't have adequate data to further cover this. Some of the lessons I learned when working with this program: 1, don't be afraid to make mistakes. 2, have a cohesive method of organization. Name your files, a very uniform thing. It'll help you out so much in the long run. And 3, work on setting a personal schedule. When your hours are sort of come in when you can, it's very hard to keep yourself reliable if you don't tell yourself, okay, I'm going to do this thing every day. And further driving home the first point, so this box right here was the bane of my existence a few days ago. While I was learning how to work the optical microscope, I was going to put a chip on the microscope, and it flew out of the tweezers into this box. So I had to spend 10 minutes sorting through these little styrofoam packing peanuts trying to find my chip. I did find it eventually, which is why we still have the tests, but when telling my mentor about it later, I was freaked out, thinking that I would be so stupid. And then she tells me that she lost a chip in there earlier too that I was able to find. So don't be afraid to make mistakes. Don't be afraid to do dumb things in lab. Everybody's human, and you'll learn more in the long run if you let yourself mess up. So steps forward with this project: we should continue collecting data on the different film systems, finish the self-healing tests, heat it in the phosphate buffer solution, and try other things outside of that. Maybe heat it to a different temperature. And also, I will be considering opportunities for presenting research, such as the poster presentation opportunity given, etc., to get more experience with presentations. Finally, some acknowledgments and thanks. Once again, I'd like to thank my mentors, Jordan Brido and Dr. Svetlana Sukashvili. I'd like to thank the previous work of the Sukashvili group for all of the relevant papers and information I needed to learn, especially Hlushko et al. 2020, Kozlovskaya et al. 2015, Shutava et al. 2006, and Zhao et al. 2013, and Dikolobus et al. I would also like to thank all O-REU mentors and collaborators for making this experience possible. Here's the works cited of the research I previously mentioned, and thank you for your time. If you have any questions, feel free to email me at allisonsmith@tamu.edu, and have a lovely afternoon. I hope you all are doing great.